Hi everybody, here's the Walter Fent applet for reflection and refraction of light waves. This is a very useful app. It's a very good tutorial app. It shows you at the same time both reflection and refraction of light waves at an interface between two materials of different indices of refraction. And it's a nice pedagogical product because it walks you through step by step different uh, ways of looking at the problem, and it asks questions and kind of gives you the answer here. It gives a narrative to go along with it. I'll walk through that narrative with you, and hopefully give you some better appreciation for reflection and refraction and what we mean by the Huygens principle. So here's the setup. We have two materials, a yellow material and a blue material. The yellow material has index of refraction N1. The blue material has index of refraction N2. So first one here is index, the way it's set up when you load it as default, has an index of refraction of 1. So this is like a very light density material, like air. 1.00000 would be a vacuum, 1.0003 would be air. This is currently set to an index refraction of 2, so that's a denser material. Glass is like 1.5, diamond is 2.4, so this is somewhere in between. And you can change the angle of incidence. You can make it an angle of incidence of 60 degrees. Here, that's a wave coming in like that. I can change it to an angle of 30 degrees, like this. Different angles. Here's the wave front coming in, so the light ray is coming this way. So I'm going to restart again. Pause. So let's walk this through step by step, and I'm going to tell you what's going on. So the first step here, it says a plane wavefront runs diagonally across the surface of two media. I'm going to change this back to 45 degrees. It's here to start. So a plane wave comes in and has different velocities in the two media because of the different index of refraction. So let me play this. Let me restart it. So here's the plane wave coming in, a single wave front. Okay, eventually this will be a train of waves, and it strikes the medium here. Okay. This is kind of tedious. This is just walking through that first step. So nothing has happened yet. Okay. That's kind of the input to the problem. All right. So now here's the next step. What happens in the next step? Let me pause it and read the material. Upon arrival at the wavefront, points along the boundary behave like little Huygens principal wavelets. Okay. Each point can be described source as a spherical source of light. Okay. So what is done here along this interface between the two material systems, we put little points, little artificial wavelet points. And every time the wave strikes one of those points, this incoming wave will launch two waves, one going this way and one going that way. This one with one speed, this one with another speed, depending on the propagation. Slower over here, faster up here. So let's let that play. Resume. And I'm going to pause it along the way. Okay, now it's just barely started to hit the first of these little Huygens principal wavelets, okay? And you can see that that launched a spherical wave going this way and a spherical wave going this way, a half sphere and a half sphere, half cylinder maybe, half circular, because this is one-dimensional, two-dimensional. This one is going faster than this one, okay? So by the time we've gone from here to here, that radius is that big. This one is smaller. Let's keep it playing. Next step. Whoops, I blew it. I'm not going to start all over again. I'm gonna skip to the next step. I should restart this and edit this out. I'm not gonna. Sorry, folks. It's been a late night. So I keep going here. Oh, here comes my train. Here comes my train. I may have to edit this out after all. Maybe I won't. So I'm going to pause here. Here's the wavefront coming along here, and here's the wavefront going along there. These small radius wavelets, these larger radius wavelengths, start to give rise to a wavefront that goes this way and a wavefront that goes that way there. Let me let that continue. Okay. Isn't that pretty? I think it's pretty. So we're just about to the end of this phase. We're putting in different pieces of the problem as time goes on. Okay, and let that play out. No, I'm impatient. Let's go on to the next step. What happens in the next step? What happens in the next step, let me pause it here, a superposition of all elementary waves results in a new plane wave. Okay, note the direction of propagation change. So let's let that resume playing here. So now we put in just what we had before, but in addition to that, the applet draws in the wavefront, draws a line across here and a line across there. This is just a pedagogical tool to show you where those wavefronts add up together. I'm going to skip to the next step. And now we superimpose on that, a pause, the ray optics diagram notation. This was the incident wavefront coming in. Here's the ray that defines that in our geometric optics case. This is the geometric ray for the angle for the reflected wave, and here's the geometric ray for the refracted wave. Okay, here's the angle of incidence between here and here. The angle from the ray coming in to the normal. That angle of incidence, which is 45 degrees, is also the angle of reflection, okay, 45 degrees. So that's as expected. Here's the angle of refraction, okay, which is 20.7 degrees. Notice, as I told you in the previous lecture, the ray always bends toward the normal in the material of higher index of refraction. Higher index of refraction, slower speed, smaller wavelengths. Let that keep playing. Resume. Okay. Now over here, we're going to start to see the little Huygens wavefronts again. Okay. This will make more sense to you after you've played it through a few times. Okay. Nothing new here except we're drawing in all those wavefronts. Okay. And you can see the incoming wave there, the reflected wave, and the refracted wave. Okay. Let's jump to the next step. Okay. A wavefront rarely comes alone. Ta-da! So now we're Steven Spielberg for Huygens principle. We're putting in all of the incident waves. Okay. It's going to get complicated, but it's going to get prettier too in a weird sort of way. Okay. Now instead of just looking at the incident, the first of that wave train, there's a continuous wave train coming in, and it goes out this way. Okay. And you can see each individual wavelet coming along there. And I think this is the end. Okay, so that's the end of the story. So let me restart all this again here and tell you what you can do with this if you really want to push your understanding. Let me pause this. Okay, let's see what happens when what I encourage you to do is to play with different indices of refraction. Okay, let's change this to 1.33. 1.33. That'll be air up here and water down here. And let me just run this real quickly. And I'm going to skip ahead, okay, so that you can see. Now you see the angle of incidence is still 45 degrees, but now the angle of refraction is 32 degrees. Next step, let's get this. I can't go fast forward here. I'm getting impatient. You guys are tired too. It's been a long semester. So what you see now is the same kind of phenomenon. Except that less bending down here. Obviously, if I made the index of refraction bigger, there'd be more bending. Here's another thing you can do. Let me restart this. Let me pause this. And instead of going from a high index of refraction to a low index of refraction, let's go from dense material here, 2.0, to 1.0 down here. That'll be just the inverse of what we had before. Same angle of incidence, but now it's going to bend in a different way. And let's let that play. Next step. And let this play. And now, because I've chosen a really big index of refraction here, I don't even get an angle, a refracted wave, okay? because I'm past the critical angle. I didn't talk about that so much in your lecture here, but if I decrease this angle now, let me pause this, pause it here, and change this from an index of refraction of 1.3. 1.3. Now we'll see both a reflected and a refracted wave. And I'm going to skip ahead, next step, next step. Okay. Now, because I'm not at the critical angle, I will get a refracted ray and a reflected wave. Okay. So there's the refracted way, there's the reflected way. If you play with this, you can get right at the critical angle where there's no refraction. All the energy goes back in the reflected way. Well, look, ladies and gentlemen, this is getting close to the end of the course. Those of you who have a real interest in optics, those of you who are photographers, those of you who want to be ophthalmologists, here's a real powerful learning tool for you to interact with. Not quite as good as being in the lab, but pretty good. So play with it and ask me any questions that I can help you with. Adios, guys.